9. Velocity and acceleration. In 1864, I think English scientist John Newlands, I love John Newlands, proposed his law of octaves, where he arranged all the discovered elements at the time in order of relative atomic mass by placing them in relative atomic masses. Newland's table was not accepted by other scientists. The periodic patterns of properties were broken down. After 5 years, when John Newlands proposed his law of octaves, a Russian chemist named Dmitry Mendeleev produced a periodic table similar to John Newland's when he arranged the elements discovered at the time in order of relative mass. However, he also discovered that the properties of elements were related to their atomic masses in a periodic way, thus forming periods and groups on our current periodic table. Through this setup, Mendeleev was able to leave gaps in the periodic table where we would expect a new element to be found in place. Thus, although not John Newlands contributed more to the discovery of the periodic table, Mendeleev is known to credit as new elements were discovered, leading Mendeleev's prediction to be right. I love John Newland's story. This was, I think, correct me if I'm wrong, but Elaine, I think you did this. So John Newland's discovery was the law of octaves. Now, if you don't know what an octave is the notes on a piano, or like essentially an octave is also the notes just in any instrument. Now I'm not a piano player, so I don't actually know everything there is to know about it, but from my understanding, it goes, and I know that a lot of you guys are much more into piano playing than I am, but from my understanding, it goes A, B, C, D, E, A, B, C, D, E, F, G, and then it goes back around. So it's A, B, C, D, E, F, G. So that's 7 notes. And then, no, A, B, C, D, E, F, G. No, I'm right, 7. Why is it called an octave then? I don't know. Anyway, point is that they repeat. And so what he did was he essentially did this idea, and then scientists made fun of him. They kept saying, oh, why don't you get your elements to play us a little tune? And essentially he never did science ever again after that, which is kind of depressing. But I really like, as I said, I think this was Elaine's job, correct me if I'm wrong. But yeah, she did a really good job. I guess sort of a great description here, sort of saying, hey, you know what, John Newland's idea wasn't stolen. It was just, made bigger. But, ultimately John Newland's is never accredited with discovering the periodic table because, even though he made a table, it's not the table that we use today. So it's an interesting story, and it's kind of like, I think it's always interesting to know, well, what did he do? Why did he do it? And he never did chemistry again, so yeah. A, B, C, D, E, F, G, A. I don't know. Anyway, that's why it's called the law of octaves. But it's an interesting story. I'd highly suggest you have a look at it if you get a chance. They used to say, why don't you get, they used to insult him. It's kind of mean. All right. So what we're going to do now is velocity acceleration. We'll be able to explain and calculate the velocity and acceleration of objects and describe their graphs. So we've got a lot of information to try and get through today. But I picked this as a double lesson. Mind you, I'm going, I think we'll make Wednesday and Thursday's lesson. We've got a bit more of a complex idea to try and teach. But I might even make one of those days just a day for you guys to catch up on some work, and then I can give you guys motion 3, which I have not given you yet. Motion 2, by the way, if you haven't finished it, needs to get uploaded and done by Thursday. Motion 1 should be completed, but as I checked the answers, out of the 20 of you that are signed up to the Google Classroom, 10 of you have done it. So there's some work there that needs to get done by a lot of people. So a bit disappointed that it's a bit late. I do understand you've got a lot of work to do already in other classes. So I'm not furious, but I'm hoping that you can get at least motion 1 done by the end of this week. That'd be good. Last time I had you guys, we were talking about graphs. we did displacement time graphs. So we looked at what a displacement time graph would look like, and then we spent a short lesson doing gradient of position time graphs. So what we did with the gradient position time graphs, we said, well, here's a position time graph. Turns out the gradient or rise or run is displacement over time, which is going to give you the speed. So that's something to keep in mind. So yeah, we're going to be using that later on. And then we talked about GPS. So today what we're going to do is we're going to tackle velocity acceleration. So let's start with velocity. We've already talked basically about it. We said that velocity was a change in how fast we are going. It's a change in position over time. It tells us how far an object has moved, so how much its displacement has changed in a given time. So let's do this now for, here we go. We're going to start with average speed first, just because I think this is a good place to start. Now, average speed equals the distance traveled divided by the time taken to travel that distance. So what we do with average speed is the total distance traveled divided by the total time taken. So it's still a change in displacement over a change of time, but the difference with average speed is this idea here: total distance divided by total time. Now, there's a pencil here, so I'd like you to copy this stuff down. But while you do that, I'll talk to you guys about this picture here. Now, averages are interesting. I always like exploring the idea of averages because students, well, maybe not students, but I know I definitely did. I used to, when I was younger, we would learn about average and mean and median and mode, and always like, why the heck do we need to know about median and mode for if average is the best one? Like, if you hear people talk about the height, they'll talk about the average height. You hear people talk about the amount of money people make. They talk about the average wage, the average age, the average life expectancy. You know, all of these are different words for average. They never say the median. I was always confused about why. Why would that be? Why do we need the other ones? This is the perfect example of why averages aren't always great. The average speed, if you've got, so here's Melbourne to Mildura. It's a long drive. It's a 6-hour drive. Been on it before. It takes a long time to get there, but it's 548 kilometers. So if I was to calculate the average speed, I would go the total distance, which is 548 kilometers, divided by 6, because it takes 6 hours to get there. A lot of it is spent, you know, there's nothing there, and it turns into a bit of a desert, but yeah. 548 divided by 6 comes out to be 91 kilometers per hour. And I always go, okay, so that's really interesting. So then that sort of tells you, well, if you, after 2 hours, you expect to be about 180 kilometers on your journey. After 3 hours, you expect to be roughly 273 kilometers on your journey. And it's a really good way to get an idea of how far you are away. But here's the problem with average, and this is the one that I always like to draw attention to, is that it's 91. Here's the question, right? And I'm going to ask you guys this. I'm going to see, I want someone to respond to this. I'm not going to move on to someone gives me an answer. Here's the question. How much time do you think a driver driving from Melbourne to Mildura, how much of that time do you think they spend going 91 kilometers an hour? How much do you think they're going exactly 91 kilometers an hour?
0.
0. Who said that?
Me.
Thanks,
Oh,
Oliver.
no, not 0, but like really less.
But yeah, pretty much 0. I love it. Sorry, I asked this question to my year 11 physics class and it took them a good 5 minutes to get the answer. So I'm actually really impressed with you, Oliver. You're on the ball. 0, barely any. The speed they're most likely going to be going on is on a freeway. It's most likely going to be 100 kilometers an hour. The reason that it's not, but if you do an average, if you do 100 kilometers an hour plus 60 kilometers an hour plus 20 kilometers an hour plus 0 kilometers an hour, if you do an average of all the speeds, you will get 91 kilometers an hour. But just because that's an average doesn't mean that that is the speed that you're going on the whole time. That's the problem with averages. The average, and this is the one that they always say, the average number of children that a family has is, I think at the moment it's 2.4 children. But that doesn't mean you'll ever find a family with 2.4 children. There'll either be like 2 children, 3 children, or like 1 child, or no children. You won't find 2.4. That's just not a thing that you'll get. And it's the even more classic example, but this requires a bit more thinking, is the average amount of legs. The average amount of legs a human being has is less than 2. Well, what do you mean less than 2? Well, if you add up all the people with 2 legs, you add up all the people with 1 leg and all the people with no legs, and you average them, the average is going to be somewhere between 0 and 2. So therefore, it's going to be less than 2. It's a bit weird, but yeah. So the idea is that I'm trying to get to, or go back to, is that the average speed is a good way of telling you generally where you're going to be and how long it's going to take you, but it's not a good way of getting the exact speed that you're going. For that, we need to use something else. But before we get there, let's take a bit of a hike. We're going to take a bit of a hike. And this is the reason we're going to put this slide up, is because I've got a lot of students that made this mistake over and over and over again in tests. So it's about time I talk to you guys about it. We're going to take a bit of a hike. And in this hike, we're going to travel 3 kilometers up a hill in 20 minutes. Okay, we're going to walk 3 kilometers uphill in 20 minutes, which is not, I think it's a doable-ish. It's a pretty fast pace, but doable. Then what we're going to do is we're going to stop for a breath. We're going to take 10 minutes to take a quick break, maybe grab a cup of tea, whatever. Then we're going to walk. He walked 4 kilometers in 30 minutes. So we're going to, like this person, this man, then walks another 4 kilometers in 30 minutes. Maybe it's not uphill anymore. What is the average speed? All right, well, let's calculate the average speed. Now, this is where people get a mistake. Let's do this together. The average speed I don't know how to do that. Let's maybe do, oops. Let's try this. Let's go with this speed, and then we're going to do a little A down the bottom for average. That's an A, not a Q. I'm struggling here, guys. Again, not having a pen makes this very, very difficult. So the average speed is going to be the total distance divided by the total time. Can someone tell me what is the total distance traveled in this question? Oh, look at that. Someone gave me an answer straight away. Oh man, the amount of times I've had to sit here and wait for hours. 7. Now, can someone tell me, oops, that's a terrible 7. Can someone now tell me what is the average, what's the total time taken? 60 minutes. So we're just going to replace this with 1 hour. Now, the reason that 7 divided by 1, which is going to be equal to 7 kilometers per hour. Now, the part that people make a mistake, and you guys might be sitting here being like, oh, that's easy. The part where people make a mistake is they forget to add this 10 minutes. They go, oh, well, he's not walking in that 10 minutes, so that shouldn't count for the average speed. But I want you to not think about that 10 minutes. Think about this. If you were at the, if you said go, and then you quickly moved to the end of the hike, 7 kilometers away, and you waited, and it took 1 hour to get there, then you would assume they traveled 7 kilometers per hour. It wouldn't matter if they took a break for 10. Wouldn't matter if they took a break for 10 minutes. Wouldn't matter if they didn't take a break for 10 minutes. They spent the whole time at a consistent 7 kilometers an hour. What's important here is, what is really important to understand is that the 7 kilometers per hour is the whole time, whole distance divided by the whole time, no matter what. Now, again, as we've said already, that doesn't mean that they were going 7 kilometers per hour for the whole time. In fact, if you were to go through it, you would work out that so the speed here is 0, whereas the speed here is actually 8 kilometers per hour. They're actually going faster than 7 kilometers an hour. And here, I think that's 9 kilometers per hour, but I have to double check. But yeah, like, you could work out these individually to work out the speed of that split second. And that has a name. Speed of the split second, the speed exactly when you are measuring it, has name is called the instantaneous speed. By the way, guys, so this is when I got a bit fancy and I tried to make all my slides look cool. Don't worry, we'll be back to boring white slides soon enough. Instantaneous speed. So what is instantaneous speed? Well, instantaneous speed, this is a speed at a split second. Okay? Now, it can be found using the gradient at a specific point at a position time graph. So you've got a position time graph, and you measure the speed at a particular point, then the gradient at a particular point, that will give you your instantaneous speed. By the way, for those of you that are doing advanced maths, or if you're not doing advanced maths and you're just interested, this also applies to curved lines. So if you've got a position time graph that looks like this, then your speed will be the gradient or the slope of the line at a particular point. So your speed would be that there, the gradient at that point. I'm not going to go into the word, I'm not going to mention the word derivative, but yeah, that's how you would, because you don't need to know that to do physics, but yeah, it's the gradient at that, of the tangent to the line at that point there. Anyway, so that's how we can use that's the difference between instantaneous and average speed. We talk about this a fair bit. Actually, let's do an example of instantaneous speed before we move too far along. If you need me to slow down, let me know, but I'm about to change the slide here. Okay, so next slide. Here's an example. No, there's no pencil here, but I just thought I would quickly talk to you guys about this example here. We could measure the speed, the instantaneous speed at any point along here. I'm actually probably not going to do this. This is normally an example that I would give for displacement, but let's do like this one, the first one, the last one. I actually gave a question like this just to my physics students just then as a bit of a warm-up question. A couple of students still got it wrong. But yeah, you guys did this very, very similar question before as well. So yeah, If we have a look at this, the change in speed is 15. That's a rise of 15 and a run of 20. So therefore, this is going to be 0.75 meters per second. Whereas if I look over here, I could see that this one is a rise of 10 in 30 seconds. So that's going to be 0.33 meters per second. But interestingly enough, you can also get the average speed. So the average speed is going to be, well, it's 100, total time is 100 seconds. Total distance is 30 meters. So average speed is going to be 30 divided by 100, or, oh my God, 0.3 meters per second. Again, still really missing that whiteboard, that electronic board here. But, you know, I need to kind of go through this on the slides. So you can sort of see 0.3 meters per second. Again, at no point in this whole graph are you actually traveling at an instantaneous speed of 0.3, but if you average all these speeds, you get it. Again, this is pretty close. 0.33 is close to 0.3 meters per second, but it's not 0.3. So again, something worth looking at. Now, okay, here's the big guy. I'm going to give you guys, I would like you to draw these two blank graphs into your book or onto a sheet or something, and then we're going to create our very first velocity time graph. Now, velocity time graph is a bit different to a displacement time graph, but that's okay. I'm going to give you guys a second to do that. I'm going to give you guys maybe 90 seconds. Yeah, I'll give you guys 90 seconds, or maybe 2 minutes. I'll give you 2 minutes to draw this. Yeah, I'm going to go fill my water bottle up. So you've got 2 minutes to draw these two graphs, and then we're going to do some work on them. Okay, well, that's about 90 seconds. It's a little bit longer. If you've already got it drawn, great, cool, excellent. You guys will be ready. While you guys are doing that, I'm going to put in some units here. Let's call that meters. Call this one seconds. Call this one meters per second. Call this one okay. Here we go. Now we're going to create a velocity time graph. Now velocity time graph is going to look very different to displacement time graph. In a displacement time graph, the higher the number, the further away you are. With a velocity time graph, the bigger the number, the faster you're traveling. Now, we're going to construct this as we go. And as we go, we're going to have to do some maths here and there. So just be prepared. We're going to start the displacement time graph with this guy. Can I get you to draw that little bit of line there? So it goes across 2 and up 1. Now, if I wanted to find the gradient of, if I want to find the velocity, I would need to find the gradient of this line. So what's the gradient of this line? Well, let's just do this. Here I've got a rise of 1 and a run of 2. So that means the gradient of this line is a half. Or it's traveling, for the first 2 seconds, it's traveling at 0.5 meters per second. So that means we need to put that onto our velocity time graph. Now, it's going a constant, it's going a constant 0.5 meters every second. So it's a stable 0.5 meters per second. So how do I draw that on our velocity time graph? Well, because it's a constant 0.5 meters per second, I'm going to draw a straight line, as straight as I can with a shaky hand. There. That represents the start. This is so much easier to do in person on a whiteboard, but still, that green line represents the start of this journey, the first 2 seconds. Because in the first 2 seconds, the speed is a constant 0.5 meters per second. Let's add something else to this graph. Let's add this line here. Can I get you guys to add this new line here? It goes up and across. So I'll get you to add that there. Okay. Once you've done that, let's do the maths. What do the maths of this one look like? Well, for this one, we've got a rise of 3. I'm going to run of 1. So that means we've got 3 meters per second. It's definitely moving a lot faster here than it was before. So that means that if it's now moving at 3 meters per second, we're going to add that to our graph. That's going to be up here, 3 meters per second. We're going to draw a straight line across from here to here, from 2 to 3. Now understand that the graph is not joined. And the reason the graph isn't joined, and you guys might be like, oh, can you do that? You actually can do that. The reason the graph isn't joined, though, is because we're assuming that you instantaneously change your speed at this point. And I'll talk about what that means and why that's impossible. But you can't instantaneously change your speed. You can't go from 0.5 meters per second to 3 meters per second in 0 time. It's just not possible. But at the moment, we're going to ignore that because we need to draw a new line. I'd like you to draw this line here. Okay, for this line here, let's go with blue. So for this line here, we've got a rise of 0. So the speed for this one, I don't even need to check it. The speed for this one is 0 meters per second. I can tell it's 0 meters per second because the distance isn't changing. Okay, the distance isn't changing. And what does 0 meters per second look like on a velocity time graph? It looks like a flat line, just like the other ones, but it's a flat line along 0. So that's going to be, for 2 seconds, it's going to be at rest. It's going to look like this. So there you go. So now it's moving 0 meters per second. And the last one is going to be this line here. So I'll get you to draw that in and then we'll work it out. Stretch. So this line here, the negative line that I've just drawn here, that's a rise, and we'll go with this one. Where is, I've lost my marker, here it is. Do this in red, so that all the house colors are represented. That's a drop, a rise in of -2, because we're going down 2, and it's a run of 1. So therefore we've got -2 meters per second, which means if I want to draw -2 meters per second, I need to go down from the, I need to go down, and that's why I got you guys to include this part here, the negative part. So therefore we're going to have a little line along here. And that is our velocity time graph. We can see it going forward at a certain speed, then it speeds up, then it stops for a while, and then it goes backwards at a fast speed. Now, before I move on, I will quickly address the issues that I'm sure maybe some of you guys are thinking. It's like, well, that looks a bit weird to be a velocity time graph. And I said to you guys, it's not possible. What the graph might look like, be more likely to look like for this situation, is something like this. And what this graph would look like, the point is that between this speed and this speed, there is a time when the speed is changing rapidly. That speed is getting faster and faster and faster in order to get to that top speed. There's also a chance in here where the speed is getting less and less and less and closer to 0 and slowing down. It's right here. That's another time where the speed is changing. And that's the rate. There is like that speed could change very slowly or very quickly. And that the steepness of that line would say how quickly that changes speed. In real world situations, those lines will be curved. So you speed up slowly, but then you'll speed up faster and faster and faster as you build up a bigger and bigger speed. And yeah, we're going to talk about that in a second, because there's actually some fundamentals here. But has anyone got any questions on what I did and how I went from a displacement time graph to a velocity time graph? Does anyone have any questions on how I did that, or anyone unclear of something? Yes, there is a question. Okay, cool. You don't connect them. No, you can. There's nothing wrong with you connecting them technically, but as you would have to connect them with straight lines. So what I would mean by straight lines, you can connect them like this. They should be connected. The only reason they're not is because, yeah, like that. That's fine. You can do this if you want. Just yeah, and then that way they're all connected, and so then it's all sort of thing. Yeah, you don't have to, as long as you've got as long as everything's covered, you should be fine. But yeah, you can connect them like that if you want. Just the point of that line though is to mention that you're instantly going from 0.5 meters per second to 3 meters per second. Hopefully you guys recognize that that's not physically possible, so that's why you would more likely have a graph like the one on the top right. Any other questions? Let's go have a look at a not real life, but let's look at an example of the velocity time graph. So when I get a velocity time graph like this in here, this one for some reason is measured in meters per minute, not meters per second, but that's okay. What I'm going to do is I'm going to add these two bars here, these two clues. Now my clues for this one are slow and fast, not near and far. So what happens in this graph is you can actually see that it's not a straight up and down thing. So what happens is we're not moving, and then we quickly speed up as speed changes. So we're actually getting faster and faster and faster. Okay. In this section here, which I'll do in yellow, where we've got the line that's flat, a lot of you guys are now used to saying, oh, it's a flat line, that means the object's not moving. In this case, that's not what it means. In this case, it means that the object is moving at a constant speed. It's going at the same speed of 60 meters per minute. Then what happens is it starts to go from very fast to very slow. It slows down, but actually it slows down and then it keeps getting, and then it slows down till but then just when it gets to zero, it starts to not just slow down, but starts to go speed up in the opposite direction, in the negative direction. It starts to go backwards. After it starts to go backwards for a while, it then stops, it doesn't turn around, it just starts going forwards again. No, it doesn't go forwards again, that's a lie too. God, see, these velocity time graphs are confusing. In this last little bit here, what you're doing is you're getting slower. You're not actually going forwards yet, you're just going backwards at a slower rate. And going backwards at a slower rate is not the same as going forwards. It's a bit complicated, but yeah, it's important to talk about, to try to understand these things. Even then, I don't really fully grasp, or I do grasp them, but I can't look at a velocity time graph, and I will probably make mistakes, but that's how you can think about it. This is why, of course, I always put clues in myself. I always put like these fast and slow clues in, because it helps me go, okay, if I'm in this line, I'm going from very fast to very slow, but I haven't changed directions yet because I haven't crossed the x-axis yet. So I'm just slowing down. So Oliver is pointing out this new idea, which is that speed is changing. We have a name for that. Now, the name for speed changing, because obviously if we want to talk about how quickly the speed changes, whether the speed is changing really quickly, are we going from 0 to 100 kilometers an hour in a couple of seconds, or are we going from 0 to 100 kilometers an hour in a couple of minutes? How quickly is that speed changing? How sharp are these lines on this velocity time graph? Are we going from 0.5 to 3 meters per second in 1 second, or in 10 seconds? And that changing of speed has a name. That name is acceleration. Acceleration is the rate at which velocity changes. So how quickly does your velocity change? It means, I'm giving you, don't worry, I'm not going to change the slide for a while. I'm going to give you guys a second to copy this down. It means speeding up or slowing down. I use these words a lot. I know that they're not the most scientific words in the world, but it kind of makes, it helps you understand what's going on. Oh, my speed is getting more and more and more. It is measured in meters per second. So therefore, when we talk about it, we talk about, or meters per second squared. There are a couple of ways to write down meters per second squared. You can write meters per second, or meters per second squared is the most popular. Or if you really like your indices, it sometimes is written like this. ms risen to the power of -2. Because if you remember, if you rise to the power of -2, it's the same as dividing it by s squared. And of course, it is a vector quantity. How do we calculate it? Acceleration equals the change in velocity over a change in time. So that means that it's the final velocity minus the initial velocity over a change in time, which is the final speed minus the initial speed. So this is stepped out till the end. So if you need to do calculations, you can. But we're going to talk a little bit more about what acceleration means before we start to really tackle some questions. So let's just get this copied down. I'm going to give you guys another, I'm going to say, minute or so to copy this down, and then we're going to jump into the next little bit. Okay, let's call it there. So unless you guys need more time. So that's what acceleration is, it's change in velocity. It's how, and like, if you're paying attention, which this isn't something that I teach in engineering maths, but if you are paying attention, if it's a change in velocity over time, then the gradient of these lines, is the acceleration. But yeah, don't worry about that. That's not something you need to know. So what does acceleration do? Now I apologize, I know there's a fair bit on this slide. That's actually on me. I really should have broken this slide up into two parts. So let's just focus on this top part first. Okay, and I've got a little animation to show you. So let's just focus on this top part first. When the acceleration is in the same direction as your velocity, your velocity will increase. In other words, you will go faster. And the hint is that it's a positive. You're adding the two things together. So what does that look like? So here we've got a car. So you go look at the red car. It's got a forward velocity. It's got a velocity to the right. Now, what's going to happen is with this velocity, as it moves to the right, we're going to add in a positive acceleration. It's in the same direction as the velocity. So watch, the velocity goes forward. It's in the same direction, so it keeps going forward. What that looks like is that the acceleration changes the speed, but what it does is it increases the speed because it adds to it, and because it's increasing the speed because it's in the same direction, you get an even bigger velocity. So you go faster. Let's break this down again. So your acceleration is in the same direction as your velocity. So it adds to your velocity, which makes you go faster. So just copy this first part here down. As I said, the part above the line. I'm going to give you guys a little bit of time to do that, and then we're going to talk about the second part. If the acceleration is in the opposite direction of your velocity. Okay, so now, if the acceleration is in the opposite direction of your velocity, so let's just say, let's take our blue car, and it's going forwards with a velocity. Now here's what's going to happen. Whoopsies. The acceleration is going to be against the direction. It's in the opposite direction. Now, when your velocity is in the opposite direction, it will decrease your speed. Your velocity will get smaller because what it does is it's negative. It subtracts from your speed or slows it down. This can be known as deceleration, but it can just be known as just acceleration, but it's negative. So it's negative acceleration, and it subtracts from them. So watch, this velocity, this acceleration will lower the velocity. In this case, it goes slower. Okay, now that doesn't necessarily always happen. Sometimes your acceleration is so far in the negative that instead of it will slow it down to the point that it starts going backwards. That's what the deceleration can do. Now I've got a real life example for this and a non-real life example for this. The real life example for this is throwing a ball in the air. Initially, when you throw that ball up, it's got a speed that's upwards, but its acceleration, and I'll draw it in, is actually downwards. So it's got a velocity upwards, but its acceleration is downwards. And what happens is that initially your ball has enough speed that it can go up into the air. But then as time goes on, and because the acceleration is in the opposite direction, it will slow it down until eventually the ball reaches the top of the arc and it's no longer moving anymore. And then when it does that, that's when the acceleration starts to speed it up in the opposite direction and it comes back down to your hand. So that's what it is. When you throw a ball up in the air, you're giving it a vertical speed, so it goes upwards. But as time goes on, acceleration will slow it down and eventually slow it down so much you'll start going backwards or start going downwards. My other example for this is not a real world example, but I always bring it up because a lot of people have experience with this, and that's my closest experience of deceleration is always from Mario Kart. Now, Mario Kart, if you guys have played Mario Kart, if you haven't played Mario Kart, it's usually the same case in most racing games. If you hold down the B button or the backwards button, it puts the brakes on. But what I always like about it is if you keep holding it down, it'll keep that deceleration. So first it'll slow you down till you stop. and then it'll start to speed you up in reverse. You will start to get faster and faster and faster in reverse in the opposite direction. And that's the sort of the difference between them, is that, you know, the negative acceleration speeds you up in the other way. So it's just a way that you can think about it, or at least it's the way that I think about it. Those two examples of acceleration. What else can I tell you? Oh, this is yeah, I will do this example. So we've got two examples, and then I think, oh, I've got, yeah, okay, cool. We actually got a lot further through this lesson than I thought we would. I was like, oh, we're never going to get to the end of this. We actually did. So we're driving. We've got two examples of acceleration. We're going to use this formula here. Okay, so let's grab a look at this formula here. Now, the other one as well, by the way, guys, I'm not going to do acceleration time graphs. I could teach you acceleration time graphs. I don't want to teach acceleration time graphs because I'm gonna, if you guys choose to do physics, you guys can learn about it there. But we're just going to leave it. We're just going to stick to position time and a little bit of velocity time. So let's do this one. You are driving 20 meters per second, and then you accelerate at 5 meters per second squared for 4 seconds. What is your final speed? Can I get you to jot that down, and then we're going to solve it. Okay, so I'm now going to cast this. So I will cast, I don't know what the proper terminology, put this on, but I'm going to use the paper this time because I'm not going to, I cannot be bothered trying to do multiple symbols with the pen. So give me a sec. Here we go. Okay, so okay, cool. So the question: you were driving, you were driving the speed of 20 meters per second, then you accelerate. Now let's jot this down. So you're driving at 20 meters per second. That means your initial speed is 20 meters per second. And I actually have a symbol for what's the word here? I actually have a symbol for that type of speed. We refer to that as u. So our initial speed is u. I'm actually going to say positive because it's a vector, so I'm going to give it a direction. I'm going to say it's positive. Then you accelerate at 5 meters per second. Now that's going to make us go faster. So this, we're going to say positive 5. We're going to say it's in the same direction. The symbol for, by the way, acceleration is a. So we're going to, and we do that for a time of 4 seconds. Time doesn't need a sign because, you know, time doesn't have a direction. So yeah. So what we want to know is we want to know what our final speed is. That's v. So the equation that we would use is, let's see if I can fit this in. A, your speed, your acceleration is your final speed minus your initial speed over time. But we don't want acceleration. We want the final speed. So I'm going to multiply both sides by t. That's going to give me AT equals V minus U. I'm going to add U to both sides. U plus AT equals V. So then I've got U, which is 20, plus A, which is 5 times 4 equals V. V equals 20 plus 20 equals 40 meters per second forward. No, it says speed, so I don't need to give a direction. Sweet, excellent, cool. So that's our working out here. So we've got initial speed, acceleration, time, final speed. Here are the symbols. Here's the equation, V minus U, or the change in speed. Change in speed over the change in time. Then we just rearranged it to solve. Are there any questions about how I did this one here? All right, next, I would like you guys to copy down the final, by the way, this is same sort of thing. What was the change in velocity, what was the new speed, whatever. I want you to copy down this last example here. Then we'll go through it. There was a question. No. I have no idea what the hell that question, that point is, but yeah, cool. All right, so you are skiing down a slope that is at 10 meters per second, and then start slowing down to 4 meters per second in 2 seconds. What is the acceleration? What is this? What will the speed be in another second? So I want you to jot that down, and then we're going to solve it. All right, let's give this a crack. So, oh, someone said no anymore. So someone's already got an answer. Let's give this a go. Again, you guys can probably do this already anyway, but let's do this anyway. Okay, here we go. So, oops. There we go. So now I'm going to start being a bit more shorthand with the symbols, but you'll be able to tell what I'm doing. So you're skiing down a slope at 10 meters per second. Okay, so we're going to say that you're skiing down the slope. Your initial speed is 10 meters per second. Okay, then you start slowing down to 4 meters per second in 2 seconds. So your final speed is 4 meters per second. And you do that change in speed in 2 seconds. And we want to work out what is the acceleration. Well, by the way, this is positive, this is still positive. So acceleration equals by the way, these signs being positive or negative, surprisingly important. I'm going to warn you guys, I'll warn you guys now, I'll warn you guys again later, but there is a question on the motion test that is designed to get you guys to get the answer wrong, because it's got the east, it goes east and west. So one of the velocities is actually negative, I might show you that example if I can find it, because I've got it written down somewhere, but I'll go through it. Yeah, I'll go through it if I can in a little bit, but we'll do this first. So acceleration equals v minus u over t. Good thing we're calculating acceleration. We don't need to change anything. 10 minus 4 divided by 2. Oops. Wrong. 4 minus 10 divided by 2. That's going to be negative 6 over 2, which is going to be negative 3 meters per second squared. Now that's interesting. Because that's a negative, that implies that whatever we're doing is slowing down, which is what's happening. We're starting at 10 meters per second, and we're going down to 4, so we are slowing down. Now the final question is, what will the speed be in another second? There's a couple of ways you could do this. You could do this the easy way or the hard way. Let's do the easy way first. If we're traveling 4 meters per second, and if we remove 3 meters per second, because we're only doing that for 1 second, our final speed will be 1 meter per second. What's the hard way, but the slightly better way would be to go like this. So our initial speed is 10. Our final speed is we don't know. Our time is not 2 seconds, but we're going to make our time 3 seconds. And our acceleration, we know our acceleration is negative 3. A equals v minus u over t, which means that at equals v minus u. V equals u plus at. By just moving the u over to the side, you get that. So that means our final speed is going to be equal to 10 plus negative 3 times 3, which is 10 minus 9, which is 1 meter per second. And sorry, you can't see. But yeah, that's the same speed, 1 meters per second, 1 meters per second. And so it's a different way of doing it, but you get the same answer. Right. Let's. Okay, so this slide got removed for some reason, so I thought I would just talk over it now really quickly. Just the importance of accelerometers. Tying what we've been talking about with regards to motion and acceleration to physical actual engineering devices, accelerometers are devices that are used to measure change in velocity very accurately. So they can be used in devices such as like phones, car airbags, planes, drones, video games, medical alert devices, and missiles even. So what is an accelerometer? Well, what it is just a small chip that allows you to measure the change in velocity in X and Y and Z. And it can measure to see how far it's been rotated in either of those directions, or if it's just moved in them. So it's really good if you place these things in phones. All modern phones have them, so it allows you to tell which way you're holding your phone. In car airbags, where they were first introduced, what they were able to do is if you were to crash into a wall, you could sense that crash into that wall as a sharp change in velocity. So therefore, that was then recorded as an impact. So then that circuit, that accelerometer, would set off an airbag. Planes and drones use the same thing. It's like if you start to pitch or roll or change your velocity or your rotation in one direction, then that would be signaling. So all drones that have self-leveling have some kind of accelerometer somehow that will allow you to measure that rotation. Now, of course, video game controllers now have a lot of these devices as well, so that you can measure them, especially if you look at Oculus Rift. You need to be able to know how the different parts of your head setup and your hand setup are moving relative to each other. So that's why you need to have really advanced accelerometers, even stuff like medical alert devices. So then if someone has a quick
fall to the ground, that information from an elderly patient or someone else can be sent to a hospital, and the hospital can send someone out quickly to check up on that person. Did they drop their bracelet or their medical alert device, or did they actually fall down and they need medical assistance? And even missiles need to have accelerometers, so they know where they are positioned in different parts of the atmosphere. So yeah, accelerometers are really useful in all of engineering devices and building devices so that you can know what your device is doing in 3 dimensions.